let's just jump right in with a pretty bold statement. Just about everything you think you know about gravity, that feeling of being pulled down, that force holding you on the Earth, it's basically wrong.
I mean, really think about that for a second. What if this fundamental thing you experience every single moment of your life isn't a force at all? What if it's something way, way stranger?
For hundreds of years, the story was simple, right? Courtesy of Isaac Newton, we thought gravity was this invisible force, a pull between any two objects. Made sense. But then Albert Einstein came along and just completely rewrote the rules. He said, no, it's not a force. It's actually a side effect of the shape of the universe. It's geometry.
Now, to really appreciate just how massive this change was, we've got to spend a minute with the old idea, the one we all learned back in school.
The old Newtonian picture is super easy to imagine. It's like the Earth and the Sun are tied together by an invisible rope. The Sun is always pulling on that rope, and that's what keeps us in orbit. It's a straight-up pull across empty space. And look, it works really, really well for a lot of things, but it is not the full story. Not even close.
So where did this elegant picture start to show some cracks? Well, it all started with one of Einstein's famous thought experiments, taking place in a simple elevator, of all places.
Okay, stick with me here. Imagine you're in a sealed elevator, no windows. So on Earth, you feel your normal weight pushing you into the floor. Easy enough. Now, let's take that same elevator and put it out in deep space, far away from everything, and hit the gas so it accelerates upwards. Inside, you'd feel the exact same sensation, the floor pushing up against your feet. There's literally no experiment you could do inside that box to tell if you were sitting on Earth or accelerating in space. And this is the core idea. Gravity and acceleration feel exactly the same. They are equivalent.
And this is the brilliant leap. See, Einstein already knew from his theory of special relativity that acceleration does weird things to space and time. It actually warps them. So his logic was, if gravity is indistinguishable from acceleration, then gravity itself must be the warping of space-time.
And just like that, this insight puts us in a whole new reality. We're not playing with invisible forces anymore. We're talking about the actual physical fabric of the universe.
You see, we used to think of the three dimensions of space, up/down, left/right, forward/back, and the one dimension of time as totally separate things. Einstein showed that's wrong. They're woven together into a single fabric. Your movement through space literally affects how you experience time. It's all one unified thing, space-time.
So, how in the world are we supposed to picture a four-dimensional fabric getting bent? It's tough. The most popular analogy, the one you've probably seen, is the rubber sheet. You stretch out a big sheet of rubber, then you drop a heavy bowling ball in the middle, and it creates this big dip, a curve in the sheet.
Now, this analogy is a great starting point, but honestly, it's also really misleading. First off, it only shows two dimensions of space being bent, and it completely ignores the warping of time, which, as we're about to see, is actually the most important part. But the biggest flaw is this. Why does a marble roll into the dip made by the bowling ball? Because of Earth's gravity pulling it down. The analogy uses the very thing it's trying to explain.
Okay, so if there's no pull and the rubber sheet model is kind of broken, then what is telling objects how to move? Well, the answer is all about the path they're taking.
The answer is a concept called a geodesic. And that's just a fancy word for the straightest possible path an object can take through a curved space. So things aren't being pulled, they're just trying to go in a straight line, but they're doing it in a universe that is itself bent.
A perfect way to get this is to think about a long-haul flight. If you look at the route on a flat map, it looks like this big, weird arc. But on a round globe, you can see that arc is actually the shortest, straightest path between 2 points. It's the exact same idea for planets. The Earth isn't being pulled by the Sun, it's just following its straightest possible path through the space-time that the Sun's massive presence is curved.
And this leads to an absolutely wild conclusion about that feeling of weight you have right now. That is not gravity pulling you down. Your body is just trying to follow its natural path, its geodesic, which is to fall freely toward the center of the Earth. Your weight is actually the force of the ground pushing up on you, getting in your way, and stopping you from taking that natural path.
But we've been talking a lot about warped space. The most profound, the most mind-bending part of all of this is that gravity doesn't just warp space, it warps time itself.
So let me ask you a question. When you drop a ball right here on Earth, is its fall caused more by the curvature of space around it or the curvature of time?
The answer is pretty shocking. It's almost entirely about time. This number you're looking at,
that tiny fraction of a second. That's how much slower a clock here on the Earth's surface runs every single year compared to a clock way out in deep space, far from gravity's grip.
Yep, you heard that right. The main effect of gravity that we experience every day is a warp in time. Things fall because they're following a path toward where time itself flows more slowly. So we're not so much being pulled through space as we are sliding down a gradient in the river of time.
Now, I know, this all sounds incredibly abstract, like something out of science fiction. But this isn't just a theory on a blackboard. The proof that we live in this warped reality is all around us.
The very first big confirmation came way back in 1919. During a solar eclipse, astronomers actually measured the light from distant stars bending as it passed by the sun, just like Einstein predicted. Today, we see this effect, called gravitational lensing, all over the cosmos. Massive galaxy clusters act like giant cosmic telescopes, bending the light from galaxies behind them into these beautiful, distorted rings and arcs. But what's even crazier is that there's proof of this in your pocket. Your GPS couldn't work without it. The satellites orbit way up high, where gravity is weaker, which means their internal clocks literally tick a tiny bit faster than ours do down here on the ground. If engineers didn't constantly correct for this time warp, your GPS would be off by miles every single day. The only reason it works at all is because Einstein was right.
So it all comes down to this really elegant two-way street. The physicist John Wheeler put it perfectly. Massive objects tell space-time how to curve, and curved space-time tells objects how to move. It's this beautiful cosmic dance.
And this leaves us with one final provocative thought. We just went through how gravity, probably the most familiar force in the universe, isn't a force at all. It's just the shape of reality. It really makes you wonder, doesn't it? What other fundamental forces out there might just be another wrinkle in the fabric of the universe, waiting for us to figure it out?